Hello, friends! Welcome back. Day 4 of the regression challenge. So, just quickly go over what we learned the first 3 days. Let me zoom in again. Every time I forget. So, day 1, we learned about 3 different types of regression: Poisson regression, linear regression, and logistic regression. Day 2, we learned about fitting a model and diagnosing it using diagnostic plots, making sure it was a good model. Day 3, we learned how to interpret model output. And today, we're going to learn about multiple regression. So far, we've just been, well, I have been. Some of y'all are already way ahead of us, and that's 100% okay. But I've just been working on predicting one output variable using one input variable. And the vast majority of the time, sort of out there in the world, when you're doing data science and analyses, you're going to want to know about multiple input variables. And knowing what multiple input variables are doing to your output variable is known as multiple regression. Oh yeah, I don't have to highlight anymore because I have the little cursor halo, I guess. Yeah. Okay. So we're going to use a sample data set, and it has information on a lot of different types of information. We're just using a couple of columns, and I am trying to predict people's BMI, so body mass index, using their height, their weight, the amount of time they spend exercising, and the amount of time they spend eating. And this is from data collected by the U.S. Bureau of Labor Statistics. Also, spoiler alert, the BMI is calculated based on your height and weight, so I expect to see a relationship using for both of those variables. And then I've also read in a data set of New York City census data for you guys to look at. And you can't see, but there's lots of really interesting things here. So it's by block. So you can look at income, you can look at sort of density, you can look at whether or not people drive, the type of work they do, all sorts of really good variables there, and a lot to unpack. So I hope you guys will have fun working with that data set. But back to BMI. So I am using 4 inputs and 1 output. And the output is this ER-BMI column. And by looking at the documentation, where there's a link to it here, I saw that that is equal to body mass index. So I'm going to predict body mass index using 4 different input variables. This one, which is for exercise frequency, how many times in the last week this person has exercised. This is for weight, so the person's weight in pounds, because it's the U.S. Census Bureau. This is height, so this person's height in inches, again, U.S. Census Bureau, so we're going to be using empirical measures. And then this is the total amount of time spent eating and drinking in minutes over the past week. Because body mass index is a continuous value, it can have sort of decimal points. I'm using a Gaussian model here, which is linear regression. And I'm using the BMI data for my data. So fitting the model, that's done. Now we're going to do some diagnostic plots. And I'm actually going to use the base R plot here rather than the glm.diag.plots that we used yesterday, or 2 days ago, sorry. And I've noticed that these have been failing a lot of the time for people on larger data sets. So plot is a little bit lighter weight, so let's go with that. And it doesn't give you quite the same output, so I'm going to go through the output here. So the first 2 are the same that you would get with the other ones. Here is residuals versus fitted. So you want this to be sort of a formless cloud, and you want this red line to be basically on this dotted gray line. And we can tell, looking at this plot, that is not the case. We can see a shape, and it's sort of like a bow tie. So what this means is for predicted values with a BMI around 30, we're pretty accurate. The residuals are pretty low. And the further we get from there, the higher the residuals are. So we're pretty accurate around the middle of the scale, and the further we get out, the worse we are. We can also see that same sort of skew in this normal QQ plot. So again, we want this line, this dotted line, to have all of our points on it, and it should ideally go from this corner to this corner in this direction. And because it doesn't, we can see that it's off here and it's off here as well. We know that there's a pretty big skew in our data. So these are telling us basically the same thing. Modeler beware. This scale location plot is new. We haven't seen this one before. So what this is showing you is for the various values that you are predicting. It's showing you a similar thing to this plot. How far off are we? So what you want to see here is you want this red line to be straight on the bottom, and you don't really want to see a pattern in these dots. And again, we see a pattern. We sort of knew that we are more accurate towards around 30 BMI and less accurate towards the sides. So this is also maybe throwing up some warning signs. Maybe we should be a little bit cautious with this model. And then this one is residuals versus leverage. And the thing that we want to look for here is we want everything to be sort of like clustered around 0 here. And we don't want any points to be on the other side of this dotted red line. And if you don't see the dotted red line, that's good. It means it's just like out here in space. So we don't have any really influential points that have a lot of leverage. So this one is giving us the go-ahead. These three are like, maybe not. And I just talk about that. I'm still going to continue investigating our model and sort of figuring it out and interpreting it, but big old caveat, we wouldn't want to use this model to make predictions for anything like far away from the mean. So we're going to look at the summary. So we learned how to read these yesterday. And the only difference with multiple regression is that you're going to have the intercept and then you're going to have multiple terms. So here is frequency, here's exercise frequency, weight, height, and then how much time they spend eating. So we can tell... So we're not actually getting a strong warning sign from the deviance residual. So this is around 0. These are pretty much symmetrical. These are a little bit off. The range is not really symmetrical, but just looking at these numbers, we wouldn't necessarily know that there was a reason to worry, which is why you want to do your diagnostic plots, because they'll tell you. All right, and we are, again, ignoring all of this nonsense. We're not looking at p-values at all. So we're just looking at the estimate and the standard error. So we're pretty sure the average BMI isn't 0, right? The intercept of BMI isn't 0. We can tell this because this estimate for the intercept is pretty far from 0, and the standard error is pretty small. So we're pretty sure that this is not 0. Also looking at it, we can tell this is pretty small. So the bigger this is, the more likely it is to be important. And also our standard error is pretty large. So it's actually larger than our estimate. So we can say with some degree of certainty, probably this exercise frequency is not that important for predicting BMI. And we can also say that probably this isn't that important for predicting BMI either. So you can actually see that this standard error is larger than the estimate again. And you can tell because this is 4 places over and this is 5 places over. So this is smaller than this. On the other hand, we can tell that weight and height are probably both important because they are pretty large comparatively, and also the errors are much smaller. So especially height seems to be very predictive. You can see the estimate is very large, the error is very small, and when you subtract the error from the estimate, or in this case add it, you don't get to 0. So just sort of looking at it, these frequency measures don't seem important, height and weight do. That's good. We know a priori that those are going to be, so we knew going in that these were going to be important, so I'm happy to see that they're important. The other thing that we can see is that adding these 4 terms really reduces our deviance by a lot. So adding these terms means that we're able to describe the variation in the data with a much higher degree of precision. So this suggests this strong difference here that these terms or some combination of these terms are really informative. And the ASC doesn't matter unless you're comparing models to each other. Okay. So now we're going to do more plotting. I love plotting. It's a really quick way of analyzing models. And we're going to do what's called an added variable plot, which is also called a, what is it? It's not piecewise regression. It's precision regression? Partial regression plots. So if you've heard of partial regression plots, it's the same thing as an added variable plot. So each of these plots tells us the influence of one of our input variables. So this one tells us the influence of this exercise frequency variable. This one tells us the influence of this weight variable. This one tells us the influence of this height variable, and this one shows us the influence of this amount of time spent eating variable. So if you, I'm going to zoom out a little bit so we can see all of these. Blip, blip. So when you're reading these, what you can read them as is if we hold all of the variables but this one steady and change this one, how is that going to affect our prediction of this one? So what this tells us is that as we change exercise frequency, it doesn't look like our prediction of body mass changes pretty much at all. So this red line is actually the coefficient. So you can see that this is the slope of this line is very close to 0, which makes sense because the slope of this line, when we looked at exercise frequency, is also very close to 0. Similarly, this value is also very close to 0. And so this is frequency of how much time you spend eating, how much time you spend eating. This is a very small number, very close to 0. The slope of this line is very shallow, very close to 0. And then these two variables, as you change them, you can see that our estimate changes a lot. So these are very informative variables, and these are not especially informative variables. And the slope of this line is positive, which we can tell because when we go up and we look at weight, we can see that our estimate is positive, and that the estimate for height is negative. And sure enough, here, the slope of the line is negative, which means it goes down as you increase x. So this tells you about the strength and direction of the relationships between your input variables and your output variables within the same model. So this is a really quick way of sort of comparing across the different variables in your model and sort of characterizing their relationship to each other. All right, so that's pretty much it. And you have a number of exercises, and it's basically do the exact same thing that you did yesterday, except A, using a new data set, and B, doing the multiple regression instead of simple regression, so adding multiple input variables to your one output variable. All right, and that's pretty much it for this. And just as a side note, you may notice that there is actually a pattern here. There's sort of a curve in this height parameter rather than a straight line like this one, or sort of no pattern like this one. And this is because this is actually related to our BMI, but it's related exponentially. So if you're interested in seeing how you can, sorry, I'm going to zoom in. So if you're interested in seeing how you can account for that, I did a second notebook that is hopefully public. Yeah, excellent, it is. That shows you how to account for that nonlinear relationship using a different distribution. So you don't have to to look at this or think about it if you're not interested. But the one thing that I do want you to get from this is that our diagnostic plots look really good once we've done this transformation. So all of these points are pretty much on this line. We don't see a pattern here. The red line is straight. We don't see a pattern here. The red line is straight. We don't even see the sort of dotted Cook's distance line in this plot. So this is a better fit for the data, and if you're interested in learning more, you're welcome to check out this notebook, but you don't have to. All right, so that's pretty much it for this introduction to multiple regression, and I look forward to... Oh, sorry, I'm still in the gamma distribution, and I look forward to seeing you guys tomorrow. Bye-bye.